So welcome everybody to our latest video on 162 Maths. In this video we'll be continuing with the theme of probability with a focus on probability trees. An alternative to listing outcomes when combining events is to draw what we call a tree diagram, with each event taking a stage of the tree diagram. So for example, what I mean by that is, if you look at the diagram you can see here, so this would be stage 1 and this would be stage 2, and what stage 3 would look like is if I had another set of branches coming from each of the ends of stage 2 branches. Now the result of, or the outcome of each event goes on the end of each branch, and the probability of the event happening goes along the branch, and at the end of the branches we need to state the series of events. Now if that makes absolutely zero sense, which it probably doesn't, let's have a look if we had this. So if we had event 1, and let's say event 1 consisted of 2 events, it consisted of A and B, whatever those 2 events are. But we've got a bit like heads and tails. And in event 2, we've got another two possible outcomes, and let's call them C and D. Now, if I was doing this as a sample space diagram, then what would the answers look like? Well, from event A, for the event 1, it'd be A and C, and then B and C, and then for the second row it would be A and D and B and D. Now representing this in a tree diagram, well, stage 1 you can either have 2 events, so let me just get rid of this dotted line. Oh, and I shouldn't have got rid of that line there, so let me bring that back and do this a little bit more carefully, like so. So here in stage 1 we've got the letters of A and B, so I've got A and B. So here, what I'll do is I would write the probability of whatever A is, and that would be in the form of a decimal or a fraction or a percentage, and this would be the probability of B. Now if A has happened first, then the 2 possible outcomes I could get from stage 2 are going to be C or D, and this would be the probability of C, this would be the probability of D. And then again, if in my first stage, if I got B, then the 2 possible outcomes in the next stage are either going to be C and D. This will be the probability of C. This would be the probability of D. Then in terms of writing down the final outcomes, so if you imagine that you always start here, and you've got a set of roads or paths that you can then go through. So going to this top branch, that's going to be A and C. Then this branch here is going to be A and D. So these are the outcomes. And to end up here, that's going to be B and C, and this is going to be B and D. And so that's what was meant by listing the outcomes and writing down the probabilities of each of the branches. Now, obviously, before we go into further, this diagram is not quite correct, because in terms of the second set of branches, this is the probability of getting C when you have A, and this is the probability of D when you have A first, and this is a probability of C when B, and this is the probability of D when B. But again, I wouldn't go into that far, because that then links into a more complicated stretch of probability and probability trees, which we'll look at later. Now, trees can consist of many stages of branches and may contain more than 2 branches in each, although it is rare to have more than 3. So what I mean by that is, for example, I could have a tree diagram where in the first event there are 3 possible options, and I then could also have another 3 options in the second stage. So your tree diagram could look something like this. It could also have a range of different events. So let's say in the first stage you could have 2 possible outcomes, but in the second stage you've then got 3. And then you could also then have a third stage in which you could have 2 sets of branches from there, or 3. But again, it all depends. So your tree diagram could be extremely big, it could be relatively simple, it all depends on the question. Now again, you do tend to find that you can't draw a probability tree with all possible probability questions, and in some cases it may not be appropriate, and sometimes you can kind of bypass a probability tree diagram or drawing one if you can kind of understand the questions mentally. Now, in terms of the types of probability tree questions you can get, now there is one in terms of independent. Now, the word independent is where the probability of an event happening is the same regardless of what stage it's in. So in other words, the probability stays the same. The outcome of one event is not linked to the outcome of another. Now, this is what we know in probability tree language as with replacement. So this is where if you had a bag of counters and it was full of either red and blue counters, then if, let's say, you pick a counter at random, the probability of red is going to be fixed, but then if you put the counter back, the probability of selecting another red is going to be the same because you're in the same situation as the first stage. Now, alternative to that is you can have what we call conditional probability. Now, this is where the probability of an event, just add a T in that, happening is affected by what has happened before it, and this is known as without replacement. So obviously, if you imagine a bag and it contains, let's say, white and for the sake of this is green counters. So let's say and I'm going to pick 2 counters. Now, the probability of selecting a green counter in the first instance is going to be 2 out of 5. Now, if I then put the counter back, the probability of selecting the green again is still going to be 2/5. However, if I've, let's say, taken one out, let's say I've picked a counter at random and it's green, then that green one disappears. And the probability now of selecting a green one on the second term is going to be affected if I've already picked a green counter in the first one. And likewise, it's also going to be affected if, let's say, I picked a white counter. Then again, the chances of selecting a green is therefore going to increase. So this is what we call conditional probability, where the probability does not remain the same after a series of events. The probability does change. Now, in terms of some general notes, it's worth making a note of. So here, sometimes a question may be explicit or obvious, which it is. So for example, a question may ask you to draw a tree diagram. It may not ask you to draw a tree diagram. So it's important that you will need to read this in the question and in the writing of the question to understand where you actually use this diagram. Now, sometimes a question may just ask you to complete the tree diagram with no further questions attached. Now, that might be stating the obvious, but you tend to find on the foundation paper that you may get a question that just asks you to complete a tree diagram, recognizing that reading the question or the tree diagram in terms of its branches and understanding it to fill it in without asking you any future probability questions. Others may need and may not need you to draw a tree diagram, but by drawing one may make the question easier to understand and answer. And again, we'll have a look at some examples of that either in this video or in the next. And this knowledge comes with practice in answering a range of probability questions from a range of resources. So don't just simply look at exam questions, don't just simply look at textbook questions, don't just look at questions from other online websites. Try and get a good range of probability questions and try and see and try and understand where it's a good time to draw a tree diagram. Another question I get asked is, does it matter whether you use decimals or fractions? With probability, I would probably stay away from percentages. Even if it does use it, I would stay away from it. But you tend to find that a question will tend to lead you to decide whether to use decimals or when to use fractions. Very rarely do they mix those two things up. So if a question gives you an initial probability in a fraction, then you would probably assume to use fractions throughout the question. If it's in decimals, then again, you'd use decimals. And finally, be sure to list all the outcomes in their order at the end of each set of branches. So we're talking about the end of a tree diagram is always try and write down what the outcome actually are in letter form. So let's have a look at drawing an actual tree diagram based on just a very simple concept. So in this, we're going to have 2 events. So we're going to have 2 levels of our tree diagram. We've got event 1, which is throwing a coin. So we can either have a head or a tail. And in event 2, we're going to pick a counter at random. And initially what I'm going to do is I'm going to start with 2 colors. So I'm going to start with green and we'll start with pink. And let's say I wanted to draw a tree diagram to represent the data from this. So for this, with event 1, now you don't need to write event 1, but I'm just going to write down event 1. So again, I've got 2 possible things that could happen. I can either get a head or I can get a tail. And the probability of getting a head on a fair coin is going to be a half, and that's going to be a probability of a half. Now the event 2 is picking a counter. Now again, I've got two possible options I could have. It's either going to be green or it's going to be pink, and the probability of picking a green is going to be 2 out of 5, and the probability of picking a pink is going to be 3 out of 5. Then completing the diagram, if I picked it through a tail on the coin, then again the two possible outcomes are going to be green and pink, and the probability of a green is going to be 2/5 and the probability of pink is going to be 3/5. Then in terms of the outcomes, so here if I end up at this stage here, then that means I've gone along this branch here and then this branch here, which gives me H and G. Finishing here is going to be H and P. Finishing here is going to be a tail and a green, and the probability here is going to be T and a tail and a pink. And that would be my completed tree diagram. Now, in terms of, let's imagine that I had, let's get rid of the colours. And let's say for argument's sake, and if we just change this up a little bit, is, and let me just get rid of this. And let's say that our choice of colours was green, pink, and red, let's say. So here from event 2, I've now got 3 possible outcomes. So here how this would change is from event 2, I would actually have 3 branches coming off it. And I would have green, pink, and red, and green, pink, and red. And again, along these, the probability of getting a red is going to be 1/5, pink is 1/5, and red is 3/5, and then 1/5, 1/5, and 3/5. And again, the outcomes are going to be HG, HP, HR, TG, TP, and TR. So you can see how completing the tree diagram would be equal as such. Now, as previously mentioned, one of the uses of drawing a tree diagram is to make it easier to find the probabilities when you are combining 2 or more events. Now, 2 words that really do come into play is and or. Now, when starting at the root of the tree, so in other words, right at the extreme left-hand side of your diagram, to find the probabilities of each of the outcomes, what you need to do is multiply the probabilities of each of the probabilities. So, for example, if I had, let's say, I'm throwing 2 coins. So I've got a head and a tail, and then on my second throw, I've got a head and a tail, head and a tail. So this is throw 1, and this represents throw 2. So here, if I'm going to get H and H, then what I would do is I would multiply this probability by this probability. So that then becomes, because I want H and H, so it becomes a half and a half, which means times. Now here, this would be T and H, or H and T. So that's going to be a half times a half, because I'm wanting this and this. And let's just stick a half there and a half there. Then for T and H, then that's going to be a half times a half, because I'm going along this branch here and then up that branch there. And T and T is going to be a half times a half. And obviously we can then work that out. Now, if a question, so to combine outcomes, we need to add the individual probabilities of the end of outcomes together. So what we're talking about here is if we wanted the probability of at least one tail, I can spell tail, which I clearly cannot, so let's just go back, of one tail. So which of these represents a tail? Well, it's either this one, or this one, or this one. So here, if I want a probability of a tail, then that's going to be HT, or TH, or TT. In which then, what I then do is I do the probability of HT, plus the probability of TH, plus the probability of TT. and that then would give me the probability of using or. So whenever you think to yourself you're using something or something, you're adding them together, and whenever you use the word and, you then multiply those probabilities. But remember, don't forget your probability scale is that all your answers when dealing with probability should be a number between 0 and 1. It should never be negative and never be a number that's greater than 1. So let's have a look at a few examples. So this question says that twins James and Rachel are taking their driving test next week. The probability that James will pass is 0.6. The probability that Rachel will pass is 0.7. And these events are independent. So what that basically means is that the chances of Rachel passing is not going to be impacted by James. There's no psychological welfare that one person's going to go back and stress the other person out, or going to give them hope in terms of one passing or the other. They are completely two separate tests that they are doing. And the question is asking us to draw and label a tree diagram to show the information. So for this, it doesn't really say who's taking their test first. So we'll just do it in the order that's written in the question. So here we're going to have James as our first event, and James can either pass or fail. And then we're going to have Rachel as our second event, and Rachel can either pass or fail, and pass or fail. And then what we then need to do is write down, as you can see, the probabilities are given us in decimals. So if the probability of James passing is 0.6, well, he can either pass or fail. So then the probability of him failing is going to be 0.4. And the probability of Rachel passing is 0.7. So that means the probability of her failing is going to be 0.3. And as we mentioned, the probabilities are independent, so they are going to be the same. And then the last thing for me to then do is just write down the outcomes. So this is going to be a pass, 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 fail, fail, and a pass, and a fail, fail. And then for B, it then says calculate the probabilities that they both pass. So the fact that they both pass, so BI, is going to be this direction here. So it's going to be 0.6 times 0.7, which gives me an answer of 0.42. Then the probability that just one of them pass, well, either I want this or this. So for number 2, it's either going to be pass fail or fail pass. Now a pass fail is going to be 0.6 times 0.3 plus, and then it's going to be a fail pass, and a fail pass is going to be 0.4 times 0.7. Then if I then work that out, I end up with 0.18 plus 0.28, which gives me an answer of 0.46. And then part 3 then says, what's the probability that neither of them pass? Well, that's going to be a fail and a fail. And so that's going to be 0.4 times 0.3, which is 0.12. Then moving on to question 2, it says that Lily throws a dice twice. She is trying to throw 6s, complete the tree diagram. So here, the probability of rolling a 6 is going to be 1 out of 6. And the probability of not a 6 is going to be 5 over 6. And on the second throw, we're going to assume it is independent. So it's going to be 1 over 6 for a 6. And not a 6 is going to be 5 over 6. And 6 and not 6 is going to be the same probability. And then here, now sometimes if you want a not event, then all you have to do is, so if S is a 6, then S dash is basically going to mean not S. So here this is going to be an S and an S. This is going to be S and not S. This is going to be not S. And S, and this is not S and not S. Now the question is then asking us to write down the probability. So this is going to be a 6 times a 6, because I'm going for this branch and this branch. This one's going to be 1/6, which is here, and 5/6. This one here is going to be 5/6 times 1/6, and this is going to be 5/6 times 5/6. Now the question's asking us to find the probability that she gets 2 6s. So 2 6s is this one here. So that's going to be 1/6 times 1/6, and writing as a fraction should make it easier. So 1 times 1 is 1, 6 times 6 is 36, and there is my final answer. Now in terms of getting 1/6, well, that's either going to be S and not S, or not S and S. So working through this is either the second or the third option. So the second option is 1/6 times 5/6 plus 5/6 times 1/6. And so working out, that gives me 5 over 36 plus 5 over 36, which gives me 10 over 36, which gives me 5 over 18. And then finally, at least 1/6. Well, that's going to be either the first, second, or the third option, or everything, basically what I don't want, which is 2 not 6s. So I can either work this out as doing SS or S and not S, or not S and S, or what I could do, that's method 1, so we could do that. Or what you could do, method 2, is work out what you don't want and take it away from 1. So it's going to be either 1 minus not S and not S. So doing it this way, it's going to be 1 minus 25 over 36, which leaves me with 11 over 36. Now alternately, if I worked out the method 1, then S and S is 1 over 36 plus S and not S, well, that's going to be 5 over 36, and not S and S, well, that's 5 over 36, and if you add them all together, you can see I get the same answer. So whichever method you pick is going to be entirely up to you. One may involve more work, but one may be quicker. All depends on that. Now this next question, it says that the probability that a bus is late is 0.25 and the probability that a train is late is 0.1. Draw a tree diagram to show the outcomes for the bus and the train. So again, here we're just going to assume whatever's mentioned first is our first event, what's mentioned second is our second event. So looking at this, we've got our bus, and that's either going to be late or not late. Now I could write that as L dash, but I'm just going to leave it as this. And then we've got the train, and again that's either going to be late or not late, and late and not late. And again, so working through the probability, so the probability of the bus being late is 0.25, so the probability of not being late is going to be 0.75, and the probability of the train being late is 0.1, so the probability of not being late is 0.9. And then the outcomes, that's going to be L and L, L and not late and late, and not late and not late. And so the question then saying, work out the probability that both the bus and the train are late. So this is going to be going through 0.25 and 0.1. So it's 0.25 times 0.1. And again, if I then just simply work that out, I get an answer of 0.025. Now for B, it then says that only the train will be late. So I'm looking for L dash as a second event. So that's either going to be this or this. So for the probability of that, it's going to be L and not L, or not L and not L. Now this probability here is going to be 0.25 times 0.9 plus, and then this event here is going to be 0.75 times 0.9. Now I would say this would probably appear on a calculator paper, but if I just work out those probabilities, so 0.25 times 0.9 gives me an answer of 0.225 plus 0.75 times 0.9 gives me an answer of 0.675, and if I add those two numbers together, I get an answer of 0.9. So now let's have a look at a conditional probability question. And these would always be regarded as a little bit higher level, so maybe worth a little few marks and may be found more later in a GCSE paper. So it says, on his way to work, Emmy has to pass through 2 traffic lights. The probability that he stops at the first set is 0.4. The probability that he stops at the second set is 0.3 if he stopped at the first set and 0.7 if he didn't. And the question's asking us to draw a tree diagram including the events and the probability. So let's do that first. So here our first event or first set of lights is our first event, and then we've got the second set of lights, which is our second event. So in this first case, he's either going to stop or not stop. And in the second set, he's either going to stop and not stop, and stop and then not stop. And in terms of the outcomes, this is going to be SS, S dash, S dash and S, and S dash, S dash. So then what we've got to do is write down the probability. So here the probability says that if he stops at the first set is going to be 0.4. So that means the probability of him not stopping in that first set is going to be 0.6. And the reason for that is you'll find that every single one of these branches should end up adding to 1, because either 1 or however many, the number of events that could happen are going to be limited. Then the second set, it then says that if he stopped in the first set, which he's done here, if I'm on this branch here, it's going to be 0.3. And if he didn't stop, the probability of stopping is going to be 0.7. So that means that those other 2 probabilities are they're going to be 0.7 and 0.3, which can be very confusing because the numbers are the same, but they're on alternate branches. So just be mindful of that. And that's part A done. The next question then says, what's the probability that Emmy stops at both lights? So in other words, I'm looking for the probability of S and S. Now that is going to be 0.4 times 0.3, which gives me an answer of 0.12. The next question then says, what's the probability that Emmy goes through both lights without stopping? Well, that's the probability of not S and not S. And that's going to be 0.6 times 0.3, which is 0.18. The next question then says, what's the probability that Emmy only stops once? Well, that's either going to be S and S dash or S dash and S. So looking at this first one, well, that's going to be the second outcome. So that's going to be 0.4 times 0.7, or means add, or this second event, which is not add, which is 0.6 times 0.3. And if I work those out, that's going to be 0.28 plus 0.18, which gives me an answer of 0.46. And there is my final answer. So hopefully that gives you a bit of an understanding, depending on the question, of when the question is going to be independent, when it's going to be independent. And you usually find that if in the branches the probabilities are the same, so as you can see in the second set, the probabilities aren't the same, stopping changes and so does not stopping, then it proves to be a little bit more thought process needs to go in, and a lot more thinking needs to go, rather than just simply going into autopilot mode and just multiplying and adding randomly.